Hello everyone, in this video, I'm going to show to you how to prove this theorem that the sample mean and sample variance are independent. Now, to prove this theorem, we need to use this lemma that if we have two random variables, let's say u and v, and they are independent to each other, then g of u, which is a function of u only, and g of v, which is a function of v only, are independent. Now let u to be a vector composed of x sub 2 minus x bar, x sub 3 minus x bar, x sub 4 minus x bar, etc. until x sub n minus x bar, where this n is the sample size. And let v to be x bar. Then from this lemma, g of u and g of v are independent. Now we have equation x bar to be equal to itself. Then if v is x bar, we can make this one as also x bar. So this x bar will be independent with g of u if these two are independent. And if we prove that the sample variance is a function of this vector only, then from here, this sample variance will be independent with this one, which is sample mean. So to prove this theorem, using this lemma, we need to do two things. First, we need to prove that this u and v, which are this and this, are independent. And the second one is to prove that the sample variance is a function of this only. So now for two things that we need to do, proving this is the easiest, so we're gonna prove this one first. That is proving that the sample variance is a function of this one only. So this is step 1. And then the independence of this and this to be step 2. So now let us do the first one. The sample variance, we can have summation of x sub I minus x bar squared from I equals 1 to n over n minus 1. Then we can extract the first term here, removing I equals 1. We have here for the over n minus 1, we have 1 over n minus 1. Then times the first term in here, which is I equals 1, we have x sub 1 minus x bar squared, then plus the remaining terms in here, which is summation of x sub I minus x bar squared from I equals 2 to n. Then in here, this term in here is a function of this already, but this one is not yet. So let us evaluate this term in here. Now for x bar, which is the sample mean, is equal to summation of x sub I from I equals 1 until n over n. Then we can do the same what we have done in here. We can extract the I equals 1 from here. So we have here, we have 1 over n times x sub 1 plus summation of x sub I from I equals 2 to n. Then from here, we can get x sub 1. If we put this n to that side, that is multiplying both sides by n, so we have here equal to nx bar. Then putting this one to that side, so we have here minus summation of x sub I from I equals 2 to n. So now x sub 1 minus x bar will be this term minus x bar. Since we have x bar in here, then this one will become n minus 1 x bar. So we have here n minus 1 x bar. Then minus summation of x sub I from I equals 2 to n. Then we know that the summation of x bar from I equals 2 to n, since the value of this x sub bar is not affected by any value of I in here, then it should be a constant for this summation. Since this is 2 to n, so we need to add this x bar n minus 1 times. So we have here n minus 1 times x bar. So we can use this one instead of this one in here. So we have here summation of x bar from I equals 2 to n minus summation of x sub I from I equals 2 to n, then equal to, we can rewrite this as summation of x bar minus x sub I from I equals 2 to n. So this is x1 minus x bar. Now what is x1 minus x bar squared? So x sub 1 minus x bar squared should be equal to the square of this term. But we know that negative y squared is equal to y squared. This is because this negative y can be factored out as negative 1 times y, and if we squared this one, it will be negative 1 squared times y squared, which is y squared. So the square of a negative variable is equal to the square of that variable. Since we are squaring this one for this term, then we can put a negative in here, and it doesn't affect the value when this one is squared. So if we put negative in here and put it inside the summation, then its effect can be interchanging the position of the variables in here. That is, it can become x sub I minus x bar. So we're gonna do that. So we have here summation of x sub I minus x bar, which is interchanging the position in here from I equals 2 to n, and this is squared. So now our sample variance will be, we have here 1 over n minus 1 times this term, which is this one. So we have here summation of x sub I minus x bar from I equals 2 to n. This is squared plus this term, summation of x sub I minus x bar squared from I equals 2 to n. So now, as you can observe, this I is from 2 to n, and also this I from 2 to n. So this sample variance is a function of x sub 2 minus x bar, x sub 3 minus x bar, etc. until x sub n minus x bar. So it is now a function of x sub 2 minus x bar, x sub 3 minus x bar, x sub 4 minus x bar, etc. until x sub n minus x bar. So now, because of this, we have proven this step 1. Let's do the step 2, that is proving that this u and v are independent. That is, this vector in here is independent with x bar. So to do that, we need to prove that this x bar is independent with each term in here. That is, we need to prove that this x bar is independent with x2 minus x bar, and this x bar is independent with x3 minus x bar, and this x bar is independent with this, and etc. until x bar independent with x sub n minus x bar. So the way we're gonna do that is just simply to prove that this x bar is independent with x sub I minus x bar, where I is from 2 until n. So now, how do we prove that this x bar and x sub I minus x bar, where I is this, are independent? One way of doing that is using the covariance. Let us put step 2 in here. We know that if x bar and x sub I minus x bar are independent, then their covariance is equal to 0. And also we know that if their covariance is 0, then they are independent. So that's what we are going to do. That is proving that their covariance is equal to 0. Now for the formula, we know that we have a general formula for covariance. Let's say we use the variables u and v again. It is equal to expectation of u minus expectation of u times v minus expectation of v. We can expand the terms in here. So we have here expectation of u times v, then u times negative expectation of v. Then we have here negative expectation of u times v. So we have here negative v times expectation of u. Then negative expectation of u times negative expectation of v. We have here plus expectation of u times expectation of v. Then distributing this expectation for each term in here, we have here expectation of uv, then minus this expectation of v is already a constant for expectation in here, so we have here expectation of u times expectation of v. Then in here, this expectation of u is already a constant for expectation in here, so we have here minus expectation of v times expectation of u. Then plus this expectation of u and expectation of v are already constants for this expectation, so we have here expectation of u times expectation of v. Now this one minus expectation of u times expectation of v, and we have here plus expectation of u times expectation of v. We can cancel them because they result in 0, so we're left with expectation of u times v minus expectation of u times expectation of v. Then for this one, we have covariance of x bar and x sub I minus x bar. So it will become this one, expectation of their product, x bar times x sub I minus x bar, then minus the product of their expectation, so we have here expectation of x bar times expectation of x sub I minus x bar. Let us evaluate this. For expectation of x bar, it is equal to expectation of x sub 1 plus x sub 2 plus x sub 3 plus etc. until x sub n. Then we have here over n. Then it is equal to, we can put this over n outside of this expectation, so we have here 1 over n. We can distribute this expectation for each term in here, so we have here expectation of x sub 1 plus expectation of x sub 2 plus expectation of x sub 3 plus etc. until expectation of x sub n. So now what are the values of this? Now the x came from here, the sampled random variables, and they should be assumed as IID. or independent and identically distributed. And we have here identically distributed means they have the same distribution, therefore they should have the same population mean and population variance. So this expectation in here should be a population mean. In here it is a population mean of x sub 1, and since x sub 1, x sub 2, x sub 3 until x sub n has the same distribution because they are IID, then we can designate each population mean as mu. So this is again mu, and also this, etc. until this. So we have here n mu's being summed. So we can have here 1 over n times n times mu. So we have here, we can cancel out this n and n, resulting in mu. So expectation of x bar will just be equal to mu. So this is mu, this expectation of x bar. Then for this one, what is the value of expectation of x sub I minus x bar? We can distribute this expectation for each term in here. We have here expectation of x sub I minus expectation of x bar. So for this expectation of x sub I, we know that it is equal to mu, then minus expectation of x bar, which is equal to mu. So this one is 0, so this one is 0. Then this whole term will just be 0. And then we're left with this for our covariance. So now covariance of x bar, x sub I minus x bar is equal to this one. Let us distribute this x bar for each term here, and also this expectation for the resulting terms in here. So we have here expectation of x bar times x sub I and then expectation of x bar times negative x bar. So we have here negative of expectation of x bar squared. Let us do this one first. So we have here expectation of x bar times x sub I equal to expectation of the summation of x sub 1 plus x sub 2 plus x sub 3 until x sub n over n times x sub I. Then from here, we can put this over n outside of this expectation, and then distribute this x sub I for each term here, and then distribute this expectation for each resulting term in here. So we have here 1 over n times expectation of x sub I times x sub 1 then plus expectation of x sub I times x sub 2 then plus expectation of x sub I times x sub 3, etc. until expectation of x sub I times x sub n. Now if I is not equal to j, then x sub I and x sub j are independent. And if they are independent, then expectation of x sub I times x sub j should be equal to expectation of x sub I times expectation of x sub j. The proof for this one is above. We know that if u and v are independent, then their covariance, which is equal to this one, is equal to 0. Expectation of uv minus expectation of u times expectation of v is equal to 0. Then we can put this one to the right. So we have expectation of u times v is equal to expectation of u times expectation of v. So we're gonna use this below. So we have this. So now in here, this is x sub I, x sub j, where j is from 1 to n and I is from 2 to n. And we know that there's only one term in here where I equals to j, and for the rest of the terms, I is not equal to j. So for the rest of the terms, they are independent. So for n-1 terms, we can put the expectation of their product as like this. And we know that this is mu, expectation of x sub I is mu, and also this one as mu. So this 2 in here is equal to mu squared. And there are n-1 terms in here where the value of the term is mu squared. So this one, expectation of x bar x sub I is equal to 1 over n times n-1 of this mu squared. Then what is left is when this x sub I in here is same with the subscript in here. So we have here expectation of x sub I squared. So now let us evaluate this expectation of x sub I squared. We know that the population variance of x sub I, we have a general formula which is expectation of x sub I minus expectation of x sub I squared, and we have a simpler formula for this population variance which is derivable from this when this term in here is expanded because of this squared in here, and then applying this expectation for its term here. The simpler formula for this population variance is expectation of x sub I squared minus square of expectation of x sub I. So expectation of x sub I squared will be equal to variance of x sub I plus square of expectation of x sub I. So from here, we know the value of this one, expectation of x sub I. This is the population mean, which is mu. But how about this one? This is the population variance. And we know that x sub I in here, where I is from 2 to n, have identical distribution, then they have the same population variance. And we can designate this population variance as sigma squared. So we have now here sigma squared plus mu squared. So for this one, which is this one, we can put here sigma squared plus mu squared. Then for this one, we have 1 over n times, we have here mu squared and another mu squared in here. So we have here n-1 plus 1 is n mu squared. Then the remaining term is sigma squared. So we have here sigma squared. Then it is equal to, we can cancel out this n and n in here. So we're left with mu squared plus sigma squared over n. So this one will be equal to mu squared plus sigma squared over n minus expectation of x bar squared. We're left with determining the value of this one for the value of our covariance. Now let us have another sheet. So we have expectation of x bar squared. We're gonna use the same formula as we have done in here. Let us use this formula. So we have variance of x bar, then we have here plus square of expectation of x bar. For this one, it is equal to this mu. This is mu. So this one will become variance of x bar plus mu squared. Now let us determine the value of the variance of sample mean. So we have here variance of x bar is equal to variance of x sub 1 plus x sub 2 plus x sub 3 plus etc. until x sub n. Then we have here over n. So now we cannot just remove this over n in here outside of this variance as we did with expectation, because variance of a times u, where this a is a constant and u is a random variable, is equal to a squared times variance of u. The reason for this one is because we have a general formula for variance. Variance of a times u is equal to expectation of that one, a times u minus the expectation of this one, expectation of a times u. Then we have here squared, and we can put here expectation of a times u minus expectation of this one. We have here a times expectation of u. So we have here squared, and we can collect similar terms in here, a, and we can move this a in here outside this expectation, but we need to square it first. So we have here a squared expectation of u minus expectation of u. Then we know this is variance of u. So we have here a squared variance of u. So we have this formula for this one. Then this one will become variance of x bar will be equal to, we can put this 1 over n outside, but we need to square it first. So we have here 1 over n squared, and then variance of this, we can distribute this variance for each term in here. So we have here variance of x sub 1 plus variance of x sub 2 plus variance of x sub 3 plus etc. until variance of x sub n. So now from here, this variance of x sub 1 is a population variance for x sub 1, and we have already designated its value, which is sigma squared. So they are sigma squared, this is sigma squared, this is sigma squared, and we have n sigma squared in here. So we have here n times sigma squared over n squared from here. So we can cancel out this n squared in here. We're left with sigma squared over n. So for this one, we have sigma squared over n. Then this one will be sigma squared over n plus mu squared. Let us use this one for this one in the previous sheet. So for this one, which is same with this one, we can use this one instead. So we have here sigma squared over n plus mu squared. Then this one minus this one, we can cancel out this one and this one and this one and this one because of this minus in here. Then this one is equal to 0. Then we have proven that the covariance of this is equal to 0, thus they are independent. So we have proven this, and then because of that, we have proven the independence of this u and v. So after proving the independence of this, and also proving that the sample variance is a function of this vector, we have proven the independence of sample mean and the sample variance. So that proves our theorem and ends this video. So I hope you learned a lot from this video and to the next video as well. So thank you for watching, and don't forget to subscribe in my channel.